Cadmium sulfide, CDs, is an inorganic compound composed of cadmium and sulfur, with the chemical formula CDS. It is a bright yellow solid that occurs naturally in two main mineral forms: greenachite, which has a hexagonal, wurtzite, crystal structure, and hauleite, which has a cubic, zinc blende, structure. CDs is a 2,Vi semiconductor, meaning it is formed from a group 2 metal and a group Vi nonmetal, and it has a direct band gap of approximately 2.42 electron volts at room temperature. This band gap makes cadmium sulfide particularly suitable for applications in optoelectronics and photovoltaics, as it can efficiently absorb and emit visible light. One of the most important industrial uses of cadmium sulfide is as a pigment known as cadmium yellow. Due to its intense color, high stability, and resistance to heat and chemical degradation, it has been used historically in paints, plastics, ceramics, and glass. However, because cadmium is a toxic heavy metal, the use of CD's pigments has declined over the years, being gradually replaced by less hazardous alternatives. Nonetheless, cadmium sulfide remains a model compound for studying pigment durability and color chemistry in the art conservation field. In electronics and materials science, CDs plays a crucial role as a semiconductor material. It is used in thin-film solar cells, typically as a window layer deposited on top of materials such as cadmium telluride, CdTe, or copper-indium gallium selenide, CIGS. In these devices, CDs acts as a buffer layer that allows light to pass through while facilitating efficient charge separation and collection at the p-n junction. Its transparency in the visible spectrum and appropriate band alignment with absorber materials make it an ideal component for such heterojunction solar cells, contributing to high conversion efficiencies. CDs is also used in photodetectors, photoconductors, and photoresistors, commonly called light-dependent resistors or LDRs, which change their electrical resistance depending on light intensity. These devices find applications in light sensors, automatic lighting controls, and imaging technologies. Another significant use of cadmium sulfide is in light-emitting diodes, LEDs, and laser diodes, where its ability to emit visible light through electron-hole recombination is exploited. CD's nanocrystals, or quantum dots, have been of great interest in recent decades due to their tunable optical properties that depend on particle size. Researchers synthesize CD's nanoparticles for applications in biological imaging, display technologies, and photocatalysis. In photocatalysis, CDs can act as a visible light-responsive catalyst for processes such as hydrogen evolution from water splitting and degradation of organic pollutants. However, its susceptibility to photocorrosion under illumination and the toxicity of cadmium limit its long-term stability and environmental safety, prompting the development of surface passivation strategies and composite systems with more stable semiconductors. From a scientific perspective, cadmium sulfide has served as a key material for fundamental studies in solid-state physics and materials chemistry. Its well-defined electronic structure, high-purity synthesis routes, and compatibility with various thin-film deposition techniques such as chemical bath deposition, sputtering, and molecular beam epitaxy make it an important reference material for understanding carrier transport, defect states, and interface phenomena in semiconductors. Despite its outstanding optoelectronic properties, the use of CDs is regulated due to cadmium's environmental and health hazards. Strict handling and disposal protocols are required in manufacturing and laboratory environments. Ongoing research continues to focus on replacing CDs with less toxic alternatives that can achieve comparable optical and electronic performance, while maintaining the efficiency of devices in which CDs traditionally played a vital role.